Hello, good morning, and welcome to today's session. Let me introduce myself to get started. My name is Evgeny. I'm a software engineering manager at Autodesk, and with me today, how you doing? And with me today, I'll have Nathan Tabor from AWS Containers team. And together, we'd like to take you through a journey of how we think about application observability and resiliency. I'll begin by introducing Autodesk and our process of cloud transformation, where we take our traditional desktop products and convert them into interconnected cloud-based applications. Talk about some of the challenges we faced along the way, and kind of a step-by-step process we've gone through to overcome these challenges and build an internal cloud platform that is hopefully reusable and applicable for your enterprise. This process starts with introducing a standardized cloud platform, making sure we have full stack observability, traceability across services, and of course, some of the resiliency patterns we can put in place between the communications of these services. Eventually introducing the concept of a service mesh, at which point Nathan will share some of the new and exciting things that Amazon's doing in the space to kind of tie the loop. But first things first, let me briefly introduce Autodesk. Now at Autodesk, we make software for people who make things. All kinds of things. Now, if you've ever driven a high-performance car or admired the architecture of a beautiful building, seen a great film, or even used a smartphone, chances are you've seen what millions of our customers do on a daily basis with the products we create. Today, we have over 220 million of these customers in a broad range of industries, from design and architecture to construction, production, media and entertainment industries with a broad suite of products. And that's what really excites me about working for Autodesk. And just to reflect back on some of my professional experience to date, prior to joining Autodesk, I used to build algorithmic trading systems for large investment banks. And if you think about the very nature of that job, it involves moving bits, creating software to move bits that in turn move dollars, create better executions in the marketplace, or better overall economic system. Many of my friends and university classmates joined the likes of Facebook, where they create software to move bits that in turn create human engagements, emotions, and connections. At Autodesk, we build software to move bits that in turn shape the very physical world we live in. The airplanes, the cars, the hotels, chances are the movies you've seen on your flight here. So I want to tie a little bit of this talk in reflecting how the systems we build as engineers impact the world we live in. And speaking of that world, I have some fascinating stats to share. As we're speaking right now, there are 400,000 people joining the middle class worldwide. Tomorrow, there will be 400,000 people joining the middle class. By next year, there will be 140 million people who would have joined the middle class worldwide. By the year of 2050, there will be 10 billion human beings on this planet. And if you think about it, all of these people will need schools, hospitals, cars, smartphones, strollers, you name it. And that's a really, really great news, great opportunity. Think of all the opportunities, new markets, new ideas, new challenges this unlocks. At the same time, speaking of challenges, it is a somewhat intimidating challenge. It's a challenge that forces us to create more and better products that have less negative environmental impact on the world. Speaking of schools and office buildings and hospitals and all that, take construction industry, for example. Today, it's a $10 trillion industry. It accounts for 13% of worldwide GDP. Yet if you talk to the experts in the field, they'll tell you that over 30% of any given construction project spend is actually wasted. The waste comes from various factors, from really complex planning to inefficient workflows that connect different stages of a construction project, to the sheer difficulty of assembling really complex structural pieces on site. Now, at the same time, on the right-hand side, you see what we're noticing is a really great pattern in the world of industrialized construction, where highly sophisticated and autonomous factories and assembly lines produce prefabricated parts that can be assembled right at the construction site. Now, What this gives us at Autodesk is a unique opportunity because we have expertise through the software products we built in both of these industries. And really the key to eliminating some of that 30% waste across the construction industry is to efficiently automating and connecting these two stages of a construction project. Now, the challenge in that, of course, is in the very nature of how construction projects are run today. If you think about it, a typical construction project today represents vast volumes of highly complex, heavily linked data. This data is stored in isolated silos and requires highly complex applications to render, constraint solve, search, and really interpret that data in a meaningful way. The key to connecting the various stages of this construction project is knocking down those monolithic applications, allowing the data to move freely between systems, and really connecting the different stages of a construction project from design to modeling, fabrication, all the way to transportation and assembly right at the construction site. Now, the best architectural pattern that we see in Autodesk to enable this type of automation is, of course, highly distributed, pluggable workflows that run in the cloud, really represented as microservices. And equally importantly, observable and resilient communications between these microservices, so we have a consistent view of the overall system. Now, speaking from experience, that transformation of taking monoliths and converting them into microservices that run in the cloud and unlock the potential of each monolithic product through an interconnected system is not trivial, to say the least. The challenges come in a wide range, wide spectrum, from making sure we have full stack observability for individual services, to consistent logging, to tracing across services, to making sure we have a way to profile and tools for telemetry of applications, essentially understanding the performance of individual pieces, but also mapping that performance to the end user experience. Standardization. Now, if you think about it, today we have thousands of engineers working in hundreds of agile teams in dozens of countries in a broad spectrum of industries. Introducing a standardized platform for them to deploy, run, and observe this broad range of products is really important and also challenging. And last but not least, retrofitting. Now, I put this as a challenge, but it's really both a challenge and a great opportunity. It's one thing to build a new system from scratch using the greatest and latest technology, which is difficult in its own way, depending on the complexity. But it's yet another challenge to take 30 years worth of IP in the industries that we've built. Things like highly complex modeling tools, constraint solvers, computational fluid dynamics and simulation, products where we have products that have been built into civil legislation and have been certified to work in highly regulated industries. Think of the potential of unlocking those products and democratizing them in the cloud through an interconnected system. Of course, that's a great opportunity, but also a challenge, because making code changes and moving them into the cloud doesn't come for free. So this journey we've taken to kind of solve this dilemma is one of 4 stages, and this is hopefully something that is repeatable depending on your enterprise. The first one is just standardizing a common cloud platform. As I mentioned, unifying the different product teams and presenting them with a common cloud platform internally. Moving on to having full stack observability, just let's worry about one service at a time, but make sure we have full traceability of how that service performs. Tie the services together using distributed tracing and unified logging, and put some of the resiliency patterns across these services to make sure we're able to prevent some outages. And I'll talk through each one in detail, beginning with a standardized cloud platform. Now, many of you have laptops open, probably have things like Office 365 and Adobe and such. Our customers, similar to that, now all of these products, they work in a cloud together. Office Syncs, Adobe, and so on and so forth. Many of our customers have design, construction, manufacturing, media, rendering tools that work much the same way across a broad range of devices. Now, introducing a common cloud platform to allow these products to synchronize and work together. And unlocking those connected workflows is really, really important, a first step. In building that, we ask ourselves some really key basic motivating questions. The first one is, how do we accelerate innovation in each industry that we serve with better, more reliable, stable, and observable releases? How do we make sure we have security and compliance locked in from the start? And how do we provide a kind of a well-lit path for developers to easily ship the products? So instead of resolving the infrastructure challenges, they focus on solving the customer problems. And what we've built is essentially, on the technical implementation side, is a cloud platform that is heavily leveraging Amazon products, and is really based on 3 key pillars: CI/CD, standardized deployment and runtime environment, and of course, underpinning all of this is a compliance framework. I'm going to go back here for a sec. On the CI/CD front, we've taken on the continuous integration side, we've taken that concept beyond, compiling your source code, but also compiling localized documentation, release notes, and such, introducing security and defect detection tools right at the compile stage. At CD's time, the continuous delivery time, we invested quite heavily into deployment risk mitigation. We've written a deployment orchestration service that integrates between Jenkins and Amazon ECS, the container service, to orchestrate blue-green deployments, provide a way for teams to easily integrate automated testing as part of their release, and of course provide developers with repeatable, easy-to-use deployment patterns. That same CI/CD platform is able to deploy containers, serverless applications, and batch workflows running on Amazon Batch. Now, what really drives this point home and how it relates to observability and resiliency is really the last point on the slide. The key metrics, so what all of the first 5 points, what they've built up to is a framework for teams to really measure themselves. And this is where we benchmark ourselves against some of the industry-leading research provided by Dora and Puppet Labs, highly recommended reading, where essentially what these researchers have done is gone out to a number of high-performing, all kinds of organizations, technology organizations. And they found certain trends that high-performing technology organizations do to have better scalable, resilient, and observable systems. Some of the key trends that they found is that organizations that deploy faster, more frequently, and with lower change failure rates generally have much more observable and resilient systems. So what we're building as part of this framework is the ability, is the process of essentially setting our product teams up for success, where they're able to measure themselves on their deployment frequency, the change failure rate, how quickly they can remediate that change, and essentially how long it takes them to put a given release through to production. Moving on to the next phase, the standardized deploy, run, and monitoring environment. So as I mentioned, we have a unified way to run multiple types of workloads, from containers to serverless to Amazon Batch. In terms of runtime environment, most of our efforts are focused on Linux today, but we're making heavy investments into Windows, largely because of that 30 years of IP and many products that we've built over decades that have tight Windows integration, and some of the GPU workloads. Now, on the infrastructure side, again, coupling with some of the great primitives that Amazon provides to us, we're on multi-tenant clusters in ECS. We have a way to do zero downtime infrastructure patching. We have a way to dynamically grow and shrink these multi-tenant container clusters using Lambdas and CloudWatch and keep some excess capacity to enable fast scaling. And of course, we've built as much of monitoring, compliance, and security controls right at the infrastructure level as much as we can. And underpinning all of this is something that is a non-negotiable for many of the markets we compete in, which is a compliance framework, which through a combination of business processes and some of the hard tools that run on the infrastructure level, we're able to do automated change management, audit trails for every release, things like attaching test evidence to our release tickets, and really streamlining the process of compliance for our product teams. So at this point, we've taken these very, at first glance, different products across different industries and gave them a framework, a standardized platform to deploy and run in the cloud. The next step for us is to really make sure that once we're running in it, once a given service is running in the cloud, we have a way to observe throughout the whole stack how a given application is doing. And here again, I'll be frank with you, we didn't find a magic pill that magically solves all the problems at once. Instead, the approach we've gone with is essentially using the right tool for the job. At the APM level, looking at your actual container application, all the way to down at the infrastructure level, the EC2 nodes, the ECS cluster that it's running in, looking at the infrastructure dependencies, integrating these different metrics into a single pane of glass, and having a unified alerting mechanism in place. Now, in terms of the monitoring tools for each layer, these are just some of the things we monitor at each layer of the stack, and the tools we use to monitor it. So at the APM level, we rely on New Relic, some of the Splunk for log aggregation, and Open Tracing for unified logging, which I'll talk about in a second. At the EC2 node, a lot of things we use are pre-baked into the AMIs, such as SysDig, Aqua for vulnerability scanning, and New Relic. But we've also found some really interesting custom failure scenarios. We've had a process of containerizing some legacy applications where we noticed strange patterns where sometimes running multiple processes within the container causes a knock-on effect, which prevents additional tasks from being launched in the host. Something that the vendor product tools we could not get to easily detect. So we've written a number of, we call them health lambdas. Lambdas that continuously run and monitor for these custom failure conditions in the cluster and take either remediating action or alerting action based on these scenarios. Moving down on the overall ECS cluster, because we run multi-tenant large clusters, we continuously run a monitor for account limits, auto-scaling group limits, and so on and so forth, make sure we don't run into them. And of course, the underlying infrastructure dependencies, making sure that the overall platform is stable. Now, you can imagine there's probably there are quite a few tools listed. It is humanly impossible to look at each tool and interpret it in a meaningful way and have a single source of truth. So we have an ongoing effort to consolidate these different monitoring and observability tools into single pane of glass. We call them dashboards that are automatically provisioned. And really, the key purpose for them is to show us a service summary view, key API metrics, some of the service dependencies and infrastructure dependencies in a humanly readable, presentable platform. Moving on to what do we do when an observability tool actually tells us that something's wrong? Now, as I mentioned, there's multiple of them on the left. These are just some of the examples. What we do is essentially funnel the alerting messages from each one of the tools into a centralized platform. Today it's ServiceNow, where we create an incident record, which involves our SOC operations center, runbook procedure, and an SME escalation if necessary through PagerDuty. Now, underpinning all of this is something we call incident to improvement process, where there's a detailed postmortem in understanding what caused the abnormal condition to occur and what can we do to improve that system. We find that to be really, really useful in building better observability as a learning journey. Now, if you take a quick step back, look at the journey so far, we've taken different products, introduced a common platform, we've introduced a way for us to look at the full stack observability for an individual service. Now what we want to do is tie the different complex inter-service calls together and be able to trace a single user interaction throughout the system. Now for that, and really the key purpose behind this is to drive these three key metrics. MTTR, mean time to recovery, so during an incident, understanding forensics, understanding what's causing the incident. Mean time between failure, driving that, improving that metric as much as possible, so insights to drive resiliency and observability. And MTTD, mean time to detect. The quicker we can detect an abnormal scenario, the better. Now, the problem, as I mentioned earlier, is we have different products written in different languages by different teams in different locations in different industries. And without a centralized log format, it is almost impossible to have a consistent way of tracing a given user interaction through a complex multi-microservice system. So what we've gone with is essentially a process of introducing a standardized log format. We've adopted Open Tracing API, Open Tracing format, which is a project under Cloud Native Computing Foundation, which really paid off because it makes it easier for us to integrate with vendor products, other SDKs, and some of the Amazon services. Here's an example of a unified logging record. At the top, you see the distributed metadata information, the span IDs that travel throughout the system as the log message travels through multiple microservices, and of course, the application log data itself. Now, what powers the unified logging effort across different compute assets, be it containers, batch, or Lambda, is a set of Amazon services that, through export through CloudWatch, a log group subscription pumping into Kinesis Firehose, and through downstream analytics and storage for this log data. Equally importantly, of course, integrating with X-Ray to visualize how a given log message or how a given user interaction travels through the system. Again, let's take a quick pause, reflect back on the journey so far. With the standardized platform, we're able to have full stack observability for individual services, tie a given user interaction through a complex set of inter-service calls throughout the system. And now what we'd really like to do is introduce resiliency patterns across these services. Now, coming back to the earlier diagram I had where we have a distributed system, all is nice and well when all these services are happy and they're communicating with each other with no problems. Unfortunately, that doesn't always happen in life, and through either a process of network failures or some downstream dependency failures, a number of services get into a degraded state. Now, many of the times, it's actually not a permanent failure. Sometimes it's just a network problem, or just a transient problem at the network, at the downstream dependencies, dependency. Sorry. And one of the worst things we can do is actually overload the downstream dependency in the case of a transient failure, and turn something that is, a temporary glitch into a full-blown outage. So what we want to do is essentially be able to monitor for these scenarios and put resiliency patterns across our microservices, from traffic shaping, intelligent traffic shaping, routing traffic to different endpoints, to rate limiting, making sure we don't overwhelm the downstream dependencies, to circuit breaking, realizing that a downstream dependency is down, and instead of bombarding it with repeated requests, actually short circuit the call and don't make it at all. Having intelligent retries, and throttling overall at the service level. And when we kind of implement the different implementation approaches, we've gone put research efforts into both options. Option one is really putting all that logic inside the SDK or library, if you will, and have it run as part of your application, essentially within the process. Option two is to have a sidecar proxy. And I'll elaborate on each. So initially, we've gone down the route of option one, and we've had a degree of success, but it became apparent that some of the challenges in going down that route and really scaling this out, given the Autodesk profile of different industries, multiple languages, and different microservices, some of these challenges became very apparent very quickly. Having to maintain SDKs in all the different languages. On the right, you see some of the subset of languages we use and databases that we use in production. Making application code changes to every microservice that participates in this. Now, of course, if you put this in the process in the SDK, it only works if everybody does it, right? It doesn't work if only 50% of the services do it. Retrofitting applications, as I mentioned earlier, is also a challenge when you have to retrofit, Fortran code or C++ code with these patterns. And of course, sometimes in particularly complex workflows, it is not always trivial to determine what all of the dependencies are. So we then investigated option 2, which is essentially offloading that into a sidecar proxy. And the way that really works is, at a high level, is we're decoupling the operational and business logic behind the system, hijacking the public-facing ports, if you will, and fronting them with a proxy that intercepts incoming and outgoing traffic, applies a set of rules to it, and then relays the call to the actual application container where your microservice is running. And that option is a lot more attractive, right? It gives us an out-of-process and language-independent way to do logging, tracing, metrics collection of how these services interact with each other, but also gives us these resiliency patterns that are consistent and do not depend on whether a given application has been retrofitted or not. It gives us a very clean separation of operational and business logic, and that can be acted upon by a different set of operators. And also gives us an easier way to integrate with legacy systems and legacy services. However, what we found is that doing a POC on a couple of microservices is one thing, but running and configuring these proxies at scale, hundreds and thousands of these proxies at scale, is hard. What we essentially need is a way to have a centralized location to configure these proxies and manage configuration of these proxies. Be able to deploy, let me take that back. Be able to adjust and dynamically the configuration of these proxies without having to redeploy each microservice and essentially bounce the ECS tasks that run the sidecar container or Kubernetes pods, if you will. Have a compatibility across different compute primitives. As I mentioned, we run ECS tasks and containers. Many of you run Kubernetes pods, batch workflows, and of course serverless applications. So a way to having a centralized location across these different compute systems is very important. And of course, what we really like to do is to have it production grade and fully managed, so we can again focus on the problems of our customers instead of really investing into this effort. Now, conceptually, if you couple a lot of these proxies, these sidecar proxies at scale, with a centralized control plane that manages the configuration of these proxies, you essentially get a concept of a service mesh. And this is why I want to introduce Nathan Tabor on stage to share some of the really, really cool and new features that Amazon's been working on, literally just launched last night, that deal with this space. Nathan?
Thanks, Evgeny.
Of course.
Thanks.
There you go.
Awesome. Thank you. Good afternoon. Awesome. So I'm going to talk a little bit about the work that Amazon's been doing in the service mesh space. And I know that everyone here today is here to hear a little bit about observability and observability for modern applications. So I'm going to talk a little bit about the work that we're doing with service mesh, how using service mesh with your applications can help you get observability and actually solve some of the hardest problems that our customers are having when trying to monitor and observe the communications between microservices, and touch a little bit on Yevgeny's point as well about how observability and resiliency in your applications really go hand in hand. You can't have one without the other, and they work together to form a stable, modern application infrastructure. So let's take a look. Yesterday, we announced AWS App Mesh. App Mesh is service mesh for AWS. It gives you observability and traffic control for your containerized microservices that are running on AWS, and it works across clusters and container services. We built App Mesh based on our experience building and running large-scale control planes for our customers, and it really is something that we believe is production grade, and we're really excited to make it available to you. So the way that App Mesh works is it configures every proxy. And it's designed to work with the sidecar proxy model that Yevgeny was just describing. It helps you implement resiliency and observability across your microservices in a consistent way. So the way that this works is that when a microservice starts, that proxy starts alongside it as a sidecar container. That proxy then goes ahead and it checks in with the App Mesh control plane, and it receives configuration information about how to connect with the other microservices and how to send data that it's monitoring in and out of your microservice up to the observability tools of your choice. So Yevgeny touched on this a second ago. Why would we use something like App Mesh versus installing libraries or SDKs for monitoring inside of our application code? Well, using this type of system reduces the work that developers need to do to make sure that the application has everything it needs to run and get full observability data by decoupling your ability to manage the application's operations from the business logic that you're writing and deploying. So the high-level point here is that if you're going to configure an observability tool, or you want to change the observability tools that you're using, you don't need to actually go ahead and redeploy all of your application code. So you can use App Mesh with any language or platform, and it helps you to simplify visibility, troubleshooting, and deployments for the whole application. So overall, App Mesh is designed to make it easier for companies to migrate to using microservices, whether you're building something that's brand new or refactoring an existing application. Let's see if this clicker, there we go. Okay. So the way that this starts to work is that you have a lot of people that are delivering intent, that need to deliver intent for how those application communications need to work and the type of data that you need to get off the applications. And so we need to deliver all that intent from the developers and from the infrastructure operators down to all your microservices. And you're not just doing this with one person, you're doing this across teams. So you need a central way to actually collect all this intent and push out all this reporting data across a very distributed application. And everything's changing too, right? You have two things that are changing. You have your intent, which is relatively static, the way that you want your microservices to communicate, the type of data that you want to pull off of your microservices is something that changes over time, but it's static in terms of the way that the actual microservices are changing. So we need a way to deliver the intent down to the microservices, but we also need a dynamic way to change how those microservices are communicating with each other and pushing data out of them for observability as the state of your system changes, as you deploy new versions, as your system scales based on demand. So one of the ways that we do this is by running the sidecar proxy for App Mesh. And App Mesh uses Envoy Proxy. Envoy Proxy is open source software. This is a really well-known proxy and is a very stable and production-proven project. It's actually a graduated project and is administered by the Cloud Native Computing Foundation, which is the same organization that administers the Kubernetes project. And it has wide community support. And importantly for this session, a lot of integrations with some of the most popular observability and monitoring, logging, and tracing tools that are out there. And this project was actually started at Lyft in 2016 to solve many of the same challenges that Lyft was seeing as they scaled, that Yevgeny was describing that they've been seeing at Autodesk. So a lot of people have also been using Envoy Proxy. It's been out for a few years. And then looking at, OK, how do we actually control these proxies? This is not a new problem. This is a problem that's been around for the last few years. And they see a need for a control plane to configure all these proxies across their application. And today there are some options like Istio that exist for standing up and running your own service mesh. A few people are actually building and running their own service meshes. But the high point about why this is really difficult to do for a lot of our customers and the reason we built App Mesh is because you need to spend a lot of development time if you're going to build your own service mesh. And if you're running an existing service mesh control plane yourself, you need to spend a lot of operations time maintaining and actually running that additional infrastructure. The other thing is that existing service mesh options are tied to deployment systems. So some of the existing service mesh options out there are actually tied to deployment systems like Kubernetes. So they use the primitives of a certain container system, and they can only run within that cluster. We wanted to design a system that worked across all container services that people were using on AWS. So both Kubernetes, Amazon EKS, AWS Fargate, and Amazon ECS. So we didn't want something that would pigeonhole people into a decision about how they were going to run their infrastructure. We also wanted something that was fully managed and easy to use so that you could gradually migrate services one at a time. One of the biggest things that we hear from our customers is that adopting something like Service Mesh is really cool. They want to have things like tracing across all their applications, or they want consistent logs and metrics from every microservice. But the difficulty of changing out their code, the difficulty of redeploying all those microservices, especially if they have tens or even hundreds of different microservices with different code bases run by different teams, is very, very overwhelming. So with AppMesh, we've designed this so that you can slowly onboard services one at a time. You don't need to use AppMesh across your entire microservices architecture all at once in order for it to work. You can start with one service at a time and slowly onboard things as your developers implement the proxy model. So kind of what I just touched on, we wanted this to work across clusters and container services. We wanted something that was built for scale and stability. And we wanted to have, and this is especially important for the observability part, lots of integrations with AWS and partner tools. And then finally, we know that no matter how many integrations we build, we're never going to cover every monitoring and observability tool that you want to use. So that's why we use an open source base. That's why we use the Envoy proxy, so that the community and AWS, we can work together with you to build more integrations and more options for monitoring and controlling your microservices. So let's look a little bit about how AppMesh works in terms of the traffic control aspects. And we'll go back into the observability in a second, because this is important and interrelated. So the important thing to know is that AppMesh is not a load balancer. When you're using this type of microservices communications, the proxies actually connect your different microservices together. And so that means that we're going to connect a microservice version running in a container directly with the other microservice version running in a different container. What AppMesh does is it sends that configuration data down to every proxy and tells those proxies how to connect. So that gives you controls to route traffic between applications. And something like this is pretty easy to do today, a simple blue-green deployment, where we have existing microservice B taking traffic from existing microservice A, and we want to deploy microservice B prime. And doing something like statically sending 20% of traffic to B prime to test it as a canary is not a really hard problem to do. But when you need to deploy a lot of things quickly, and you want to be able to dynamically change your infrastructure, you may want to do things that are a little bit more complicated. And so we need the ability to actually not just put 20% of our traffic, but to do something like 3% or 2% or 1% of our traffic onto our new microservice version and dynamically adjust how much traffic is going to that microservice as we show health and performance from our new microservice version. Of course, you could also do this using a load balancer today, but the dynamicism and the intelligent routing decision-making is just not there. You would have to go into that load balancer and constantly adjust the weighting that's going to the new microservice version to get this to work. And that's just a lot of work that we don't believe is necessary to do. So AppMesh gives you a lot of traffic controls for resiliency. These were similar to exactly what Yevgeny was talking about a few minutes ago. So things like retries, where we set the number of times that a microservice can ping another service before we try and fall back to a different option. Timeouts, where we actually make a decision to stop trying after a certain amount of time. And routing controls like rate limits and waits, where we can determine how many times a minute something can call another thing, or like we were talking about in the deployment example, what % of traffic do we want to send to a version of a microservice versus a different version of a microservice. In terms of availability, AppMesh, because that proxy is consistent, so the proxy is exactly the same across every microservice, and it handles all the traffic for the microservice. And what that means is that you already have the ability to really monitor the rest of your stack. You have the ability to monitor your compute resources, like your EC2 instances. You have the ability to monitor your containers and see which containers are running. But that communications logic, debugging those tail latencies between different microservices is really tricky. And by putting that proxy next to all of our microservices, we are actually capturing all of the communications data that's going in and out of every single microservice in a consistent way. And what AppMesh can do is it can tell all of those proxies where they need to send that data. So things like statistics for latencies, HTTP header and tracing information for tracing. And you can send that to existing tools and dashboards with a lot more detail and with really good consistency. So instead of having a team that's implemented their monitoring, logging, and tracing in one way for your application, and then another team that's building a different microservice, and they happen to have set it up just slightly different, with AppMesh, you can maintain that individuality between teams. Those teams don't need to actually do anything different with regards to how they're building and running their application, but you can get consistent metrics, logs, and traces across all of your microservices. So today we have a few things that we're launching with, CloudWatch, X-Ray, and we were really excited yesterday to announce an integration with Datadog to send all of your AppMesh statistics from your microservices up to Datadog. And we're going to be quickly adding a lot more integrations over time. So the goal here is that we're going to give you end-to-end visibility across all of your microservices in a dynamic fashion without forcing your teams to change the way that they're writing, deploying, and operating their microservices. And that's really important because we need the ability to change how we send things down to our microservices without forcing all of our microservice teams to change what they're doing. If we have to coordinate across a lot of teams, if you have to redeploy application code every time that you need to change the way that you're monitoring something or you need to change how a deployment works, that's something that slows an organization down and we believe is undifferentiated heavy lifting that is just not necessary. So let's take a deeper dive, so to speak, and peel back the onion and take a look into how AppMesh works. So the way that AppMesh works is by building a virtual map of your microservices that define how the communications flow between the microservices. And what you do is you use the AppMesh APIs to actually model the different microservices in the AppMesh control plane and model how the traffic flows between them. So on the left here, we have our actual microservices. These microservices are fronted by a load balancer. So this load balancer is taking all the external traffic into our application, and then AppMesh is handling the communications between microservices within our application. Each microservice version is represented in the AppMesh API as what we call a virtual node. And these virtual nodes, we define routes between these virtual nodes to determine how we want those microservices to communicate. So a virtual node is that logical representation of a runtime service, and it has a few back-end infrastructure components, listeners, service discoveries, and backends. And so listeners are the policies that handle incoming traffic for that virtual node. Service discovery describes how other microservice versions that are calling this virtual node can locate it. And backends are a set of destinations that the node can communicate with. And so this is a virtual representation of how we actually build our communications between our microservices and AppMesh. And the way that AppMesh works is that after you build this virtual representation of your communications within the API, it computes all the configuration information dynamically that the proxies need to know in order to implement this map of communications, and it sends all that information dynamically down to the proxies. And so a virtual router is another construct that we have, and a virtual router is associated with a set of services. So your nodes are associated with the service versions, and the virtual router is associated with the actual microservice itself. So this is similar to an ECS service or a Kubernetes service. And the virtual router contains a set of rules that define how traffic is routed to all the different virtual nodes associated with the services. So a route is scoped under a virtual router. And you can define lots of routes between your nodes to explicitly and dynamically configure how that traffic is flowing between things. So each route defines an action that targets one or more of these virtual nodes. Great. So it's a little more deeper here. So in this example, we're actually taking, to implement the communications architecture on the left, we have our HTTP routes under this virtual router, and we're matching on the prefix slash, so all incoming traffic that's coming in or leaving, technically leaving microservice A, or the virtual node for microservice A. And then the target is microservice virtual node B. And so we're taking all the traffic that's leaving A, and we're going to send it out to virtual node B. And these are HTTP routes that we define. So going back to our deployment example, we can add another route within this virtual router for node A, and we can accept all of the traffic that's coming off of node A, and then we can route that with weights to two other virtual nodes. The virtual node that represents microservice version B, which is our existing microservice, and then we can add that 3% or that 5% weighted traffic going to microservice version B prime, which is our new microservice deployment. So all of this is written using API commands to the AppMesh API, and so you can actually program this in the API and then dynamically adjust it. And every time you make a change in the API, AppMesh recomputes and calculates what all that configuration needs to be at the proxy level and sends that down to all the relevant proxies that are running for the different microservice versions so that you can dynamically adjust how traffic is flowing between these microservice versions when you're doing a deployment. And so we get something that looks a little bit like this. Great. So a little bit about kind of how this works together. So these are the primitives that AppMesh is built on in the control plane. And we can put those primitives together to represent much more complex microservices. Clearly, this is still a pretty simple example of how microservices communicate. But using these primitives, we can build a dynamic map of how we want all of our microservices to communicate. And we can change that over time, and we can change that very quickly as the communications change. At the same time, like we talked about earlier, there's that static configuration that we're delivering to AppMesh that will be recomputed dynamically and change your communications patterns. But there's also the dynamic nature of when different proxies come online or different microservices scale, AppMesh will automatically send the appropriate configuration information down to those microservices so that they can dynamically join the mesh and have all the traffic routing rules applied. And that works for observability as well. So when something joins the mesh, it will automatically check in with the application or the AppMesh control plane, receive the configuration information it needs to start sending observability data, and then go ahead and start piping that observability data directly from the proxy into the monitoring, tracing, and logging tools of your choice. So AppMesh is available today as a preview for all customers. It gives you observability and traffic control. And it's compatible with the managed container services, including self-managed Kubernetes on EC2 that are being used on AWS. It's available in 4 regions today: US East 1, US East 2, US West 2, and EU West 1. So we have a nice global coverage that you can start trying this out. And AppMesh's preview today, we're planning to have AppMesh become generally available in the first half of 2019. And until that time, we'll be quickly adding new features and functionality, new integrations for observability. I mentioned that yesterday we announced an integration with Datadog for monitoring and tracing your microservices with Datadog. And we're going to be adding new integrations and new monitoring integrations along that same line over the next few months as we prepare for GA. You can learn more at our webpage, amazon.com/AppMesh. And we also have a GitHub repo where we've posted examples and more information, including a public roadmap about how we plan to evolve the capabilities of AppMesh. So here's a few more links for more resources. So really appreciate the time that you've taken today. We're going to go ahead and wrap up here. And we're really excited for you to try out AppMesh. Try it out with your microservices. Give it a shot. Visit us on GitHub. We're accepting issues there. If you have any problems or if you have any integrations that you'd recommend us or you'd like us to implement, please let us know. We're really excited about this service, and we really hope that you have a great time using it and implementing observability and control for all of your microservices on AWS. Thank you.